Hello guys, I hope you are happy and fine at your place. Today we will be studying about classification of solids based on arrangement of their constituent particles. So we will be classifying solids on the basis of the arrangement of the particles inside it. Okay, how they are arranged and how they are classified, we will be studying this. So solids on the basis of the arrangement of the constant particles are classified into crystalline solid and amorphous solid. The arrangement of particles in crystalline solid looks something like that, and the arrangement of particles in amorphous solids looks like this. We will be studying in detail the arrangement of particles in both these solids. The example of crystalline solid is table salt. The example of amorphous solid is cotton candy. Another important example of crystalline solid is diamond. And another important example of amorphous solid is your glass. So let's see the properties of crystalline solid and amorphous solid. Crystalline solids. The structure of crystalline solids looks like this. Here you can see a perfect order, a perfect rearrangement, whereas here in amorphous solids, the order is not perfect, very random. It is very random. Okay, so the first property of crystalline solids is that regular 3D arrangement of particles are there. You can see here regular arrangement is there, ordered arrangement is there, and because of this ordered arrangement they have well-defined shape. They have well-defined shape, whereas in case of amorphous solids they do not have regular arrangement. You can see here in amorphous solids no regular arrangement is there, and that's why no defined shape is there. No defined shape is there in case of amorphous solids. Second property is that crystalline solids show long range order. You can see here the same pattern is getting repeated and repeated. A long range order of materials of particles are there. Here in case of amorphous solids the pattern is only getting repeated here, but there is a disorder everywhere else. So this means that amorphous solids are having a short range order, whereas crystalline solids are having a long range order. The next property is the classification based on difference in isotropy of solids, like how crystalline solids and amorphous solids differ in terms of isotropy. But first of all, let us understand what exactly is isotropy. Isotropy. So, physical properties when measured in different directions give some value. For example, if we measure physical properties around this axis, let's say we have measured refractive index, which is represented by the symbol nu. Okay, when we are measuring refractive index of a substance along this axis, which is the axis A, we get some value, and when we measure refractive index along this axis, which is the axis B, we get another value. So if the two values, if the two values derived from measuring physical property along A axis and along B axis are same, then it is said to be isotropic. And but in case of crystalline solids, the physical properties measured along different directions are not same. That is why they are called anisotropic. I will repeat this again for you. We say that crystalline solids are anisotropic. And what anisotropic means? anisotropic means that physical properties measurements are not same along all directions. Like if physical properties are measured along axis x, y or z, the values we got would not be same, and this is termed as anisotropic. Whereas we say that amorphous solids are isotropic. And what is the meaning of isotropic? Isotropic means that physical properties measurements are same along all directions. So, in case of amorphous solids, when we measure physical properties along x-axis, when we measure along y-axis, and when we measure along z-axis, all the properties, all the values remain same. Whereas they are not same in the case of crystalline solids. Now coming to the question, why the properties are not same along all directions in crystalline solids? Earlier we have said that crystalline solids are having an ordered rearrangement, but now we are saying that physical properties are not same along all directions. So why it is so? Let me explain this with the help of this structure. You can see here the pink balls. The pink balls here represents a particular type of particle, and the green ball here represents another particular type of particle. Let's measure a physical property against a refractive index along this axis, like along this pink particles. Okay. So we will get one value from it. Whereas if we measure physical properties along this, we will get another value. And if we measure physical properties like this through this axis, we will get another value. See here, the pattern of all the three axes is different. This pattern was containing all pink balls. I repeat, this pattern was containing only pink balls or pink particles. That's why it was having one property or one value of physical property. And this is having only green balls. That's why it is having only one fixed value of a physical property. This is having both pink and green balls. So it will also be having one definite property or one value of property. And so when measured overall, we got to know that physical properties measurements are not same along all directions because every pattern is having a unique value. Next, let's see the case of amorphous solids. In amorphous solids, no fixed order is there. You can see here two green balls are there, one pink and then one again green. But if we measure along this axis, so many random arrangement is there. No particular order is there. So any row or any axis cannot obtain its perfect physical property. Like the rows in it was giving. So since a disorder is there, in amorphous solids, all the physical properties measured along all the axes gets averaged out, and overall they are same along all the directions. So this is the property of amorphous solids. Amorphous solids are isotropic, whereas crystalline solids are anisotropic. Let's come on to the next property, which is the difference in heat of fusion and difference in melting point of crystalline solids and amorphous solids. Crystalline solids. Crystalline solids have fixed heat of fusion and sharp melting point. Now what do you mean by heat of fusion? Let me explain it. Whenever a solid, let's say ice, is given some heat, it converts into a liquid, let's say water. So, but the heat absorbed by this solid to convert into this liquid is called the heat of fusion. Okay, and the temperature at which this solid entirely melts and gets converted into liquid is called the melting point. Okay, so in the case of crystalline solids, we noticed that crystalline solids are having a fixed heat of fusion and a sharp melting point. Now, what do you mean by a sharp melting point? Sharp melting point means, let's say a particular temperature is there. Let's say at 50 degrees Celsius, something is getting converted into liquid. So, only at 50 degrees Celsius. So, it is a sharp melting point. A particular temperature is there. Also, fixed heat of fusion means, let's say, suppose 100 kilojoule per mole heat is required to convert that solid into liquid. It is fixed. In case of amorphous solids, they do not have fixed value of temperature and heat of fusion. So neither temperature is fixed nor heat of fusion is fixed. A range is there. Transformation can seen over a range of temperature and heat energy. Now what is the range? Range means that amorphous solids, suppose they get converted into liquid at a range of temperature. Range here means 10 degrees Celsius to 20 degrees Celsius, 30 degrees Celsius to 40 degrees Celsius. Whenever the word 2 comes or a range is defined, it is called a range. So amorphous solids is not having a fixed value, but it is having a range. Same with heat of fusion. Heat of fusion was the heat required to convert solids into liquids. And in the case of amorphous solids as well, the heat of fusion is not fixed, but a range is there. For example, the heat required to convert the solid is, suppose, 100 kilojoule per mole to 200 kilojoule per mole. Again, a range is there. So this was the property of this was the difference in heat of fusion and melting point of crystalline solids and amorphous solids. Let's come on to the next property now. Difference in cooling curves. What exactly is a cooling curve? Let's understand it by understanding what is cooling. So cooling in general terms means that when a substance is given a temperature very low and then with respect to time the temperature is lowered and further lowered and further lowered. Cooling is simply this, providing low temperature with respect to time. And what is cooling curve? Simply providing low temperature with respect to time. Here is an example of a cooling curve. Let's understand the cooling curve with this graphical representation. Cooling curve is basically graphical representation only. So you see here, as the temperature is getting decreased, as the time is getting increased, the temperature is getting decreased. The graph is downwards. So at a particular time, suppose this temperature of a substance is this. Okay. Then when time is extended, at later point of time, the temperature is decreased. Again at later point of time, temperature is decreased. Again at later point of time, here is the minimum temperature at maximum time. This is the minimum temperature at maximum time. So cooling is taking place, and this is called a cooling curve. Basically a graphical representation of a cooling of a substance, and graphical representation is temperature versus time. Let's understand the property of crystalline solids and their cooling curve. So crystalline solids show two breaks in cooling curve. Here you can see the difference. The cooling curve of crystalline solids is having two breaks. One break is here and one break is here. And here we see that it is having a constant. Why it is so? It is so because suppose at this point there is some liquid. And for a liquid to get converted into crystals, for example, ice is there. To convert ice, for example, water is there. To convert water into ice, we freeze it. We lower the temperature. So for anything to get converted into crystals, we lower its temperature. For example, this is a liquid and we want to liquid substance or liquid chemical and we want it into crystals, what we will do? We will lower down the temperature. So at a particular time its temperature is this, but after the time is getting extended, its temperature decreases. But a point is reached where the time is increasing but the temperature remains constant. This can be shown from here. You can see that in case of crystalline solids, time increases, temperature decreases, but temperature remains constant for a particular time period. This is where crystallization takes place. And what exactly happens during a crystallization? When, say at this point, the crystals started to form. The crystals are starting to form at this point, and whenever the crystals are starting to form, they release some internal energy. They release their heat. But we are providing low temperature. We are cooling down it. Temperature externally, we are cooling down the temperature. But internally, the particle, the substances is releasing heat. So it nullifies. Overall, during crystallization, heat is increased internally, but externally temperature is lowered. Externally we are cooling, but internally heat is increasing. That's why nullification takes place and the temperature for some time remains constant. And the temperature remains constant till all the crystals get formed. So we can see here, we can say from this graph that at this point of time crystals are beginning to form, whereas at this point of time the crystals have stopped forming. All the crystals have been formed, and then this is the temperature of the formed crystals. So we see that crystalline solids show 2 breaks in cooling curve, whereas it isn't the case with amorphous solids. Amorphous solids show smooth cooling curve. This was the property of cooling curves of crystalline and amorphous solids. Now the property of cutting crystalline and amorphous solids with sharp tools. When we cut crystalline solids with sharp tool, we get perfect and plain and smooth new surfaces. For example, diamond. When we cut diamond into 2 pieces, perfect, smooth and plain new pieces are formed. That's why we are able to convert diamond into beautiful rings like this. We are able to cut diamonds and can get ordered and plain and smooth surfaces. But this isn't the case of amorphous solids. In amorphous solids, what is the example of amorphous solids? Say glass. So whenever you see a glass being broken, various irregular and rough surfaces are generated. This is an image of a broken glass. So when amorphous solids are cut with sharp tool, they cut into 2 pieces with irregular surfaces. Irregular surfaces are generated. This was all about amorphous and crystalline solids. Let's have a quick look on the conclusion of what we studied in this video. The first point, we studied about regular 3D arrangement of particles. Here it is about crystalline solids. And here it is about amorphous solids. So the first point was that regular 3D arrangement of particles was there in crystalline solids, and amorphous solids were not having regular 3D arrangement of particles. The second point was crystalline solids were having sharp melting point, amorphous solids were not having sharp melting point. Okay. Crystalline solids were having a long range order. Third point was, whereas amorphous was having a short range order. Fixed and high heat of fusion in crystalline solids. They do not have high and fixed heat of fusion, the amorphous solids. And the important one, crystalline solids are anisotropic, whereas amorphous solids are isotropic. Crystalline solids are true solids. Amorphous solids are pseudo solids. Or in the cooling curves of crystalline solids, two breaks were observed, whereas amorphous solids show a very smooth cooling curve. Crystalline solids are more stable, amorphous solids are less stable. When cut into two pieces, new generated crystals are smooth and plain, whereas in the case of amorphous solids, when cut into two pieces, the surfaces generated are irregular and rough. So these were the points we discussed in this video. Hope to see you in another video too. Thank you so much.